All right, welcome to Lab 10. We are in double-digit land now. This is called Rotational Dynamics. You know, when you go to the amusement park, there's a lot of rotating rides. Make sure you haven't had too many corn dogs before you get on them. But anyway, this is called the classic zipper right there. So you get spinning like that, and the whole thing goes around this rack here, and the whole thing turns. Crazy. Lots of rotation. All right, but you see that axis right there, that axis doesn't move. All right, so we're going to study rotation, not that complicated, but we're going to be rotating around a fixed axis, and the object that's rotating is a rigid body. This would actually not be called a rigid body because these little cars are moving on that track right there. But if it was all just one big unit spinning around that point, it would be called a rigid body. This one over here, this is the Flying Swings. This is a fantastic ride. If you've never been on one before, it's spectacular because you see, in order to go around at uniform circular motion, you need an inward force to do that. So the swing has to go out at an angle, so you have a component of the tension in towards the center of the circle. All right, so anyway, it's called Rotational Dynamics, and it's based on rigid bodies. That means all the relative points on the body remain fixed in relation to each other, okay? All right, now this guy over here, he's taking a swipe at a ball, and in his hand is a bat. He's also got this arm, his two arms right there that are attached to the bat. And that motion of the bat, you see he's putting torque on it. The torque is being applied right there at the handle of the bat. The axis of rotation is his shoulders. You can see how his shoulders are basically rotating about his head there. And so the force is in close to the axis of rotation, and it's providing a torque, making his arms and the bat swing. Now, if you've ever seen different mass bats, when you head to a major league bat, they put an awful lot of mass way out there at the end of the bat. That makes it pretty tough to swing because when you want a mass to go at a certain speed, you have to give it kinetic energy. So your ATPs in your muscle has to deliver that energy. So the further away you are from the axis of rotation, the more energy you need to make it move at a certain speed. All right, so that's a very, very important concept. All right. Anyway, I got two devices here. We'll have these in lab so you can play with them, or I'll bring them to class. Actually, with the whole COVID thing, we'll have to clean it every single time someone else wants to use it. Use it at your own risk. Okay, this guy right here, he's got mass that's distributed all the way out from the center to the ends. It's a lot harder to turn this thing, so I'm just taking this thing, turning it like that. And then the red one here, all the mass is in my hand. So you can see, it takes like nothing to make it rotate, even though they're the same mass. So when we deal with torques, making things accelerate in angle, torque's all about rotational forces. Rotational forces produce angular acceleration, which we use the same letter A, but we use the Greek A, which is alpha. So the distribution of the mass that you're torquing on is a very important factor in what kind of motion you're going to see. Okay, so that's a lot of words right there. You may want to play the old reset button, replay that and a couple of times and listen to what I'm saying. And then we'll move on to the next slide, which will go into more detail. By the way, torque, when you supply a torque, you apply a force at a distance r from the axis of rotation. So like this guy again, there's his axis of rotation, and the distance r is out to his hands right there. So he's supplying a torque. Now he wants that bat to go as fast as possible, so he is going to supply that force perpendicular to the radius to get the maximum torque. So sine theta would be 90 degrees. We're going to do the same thing in our lab. we're going to make the force perpendicular to the radius. Anyway, if there is a net torque, it'll cause the rigid body to accelerate at alpha times this thing that's related to the mass distribution, and it's called the moment of inertia. Moment of inertia. Okay? So the distribution of the mass is critical, and it's all wrapped up in that I, because every distribution of mass has a different moment of inertia. All right. So I is the moment of inertia, and it's similar to mass, but it depends on its distribution, whereas mass doesn't matter, okay? When F equals ma, we're not talking about rigid bodies. We treat everything, when we use F net equals ma, we treat everything like they're point masses. Okay, so there isn't a distribution factor. Okay, so here's a little bit more detail. So I got my rigid body. This is Mr. Potato Nose right there. And that's the axis of rotation right there. Now this might not be the center of mass of the object. So we're going to do two experiments today. One, we're going to rotate around the center mass of the object. And then another one, we're just going to rotate around some other point. Well, if you go a certain distance from the axis of rotation and it's spinning, then out there it's spinning at a certain number of radians per second, so omega is the number of radians per second, then at this point right here it's going to be traveling so fast, and the further you go out, it's going to be going faster and faster and faster. Well, why is that? Well, it's got to get around in the same amount of time. Remember, it's a rigid body, so all the relative points have to remain connected. So like when the Earth rotates every day, the North Pole area, the point where the Earth rotates around, they don't have any motion at all at the North Pole. But at the equator's got to get all the way around a 26,000 mile circumference in 24 hours. So the equator's going about 1,000 miles per hour. In Phoenix, it's about 700 miles per hour. Okay, does that make sense? All right. Anyway, S equals r theta. Remember, the arc of a circle, S, is related to the angle, and r, S equals r theta. So if you take the derivative of that, then you get the velocity, ds dt. And r's not changing. This point right here, r doesn't change. So you just have r times d theta dt. Because remember, S is r times theta. And d theta dt is called omega, the angular velocity. How many radians per second it's going. If we take another derivative, and again, we're looking at the change in velocity as a function of time, we're asking for the tangential acceleration. That's different from centripetal acceleration, and I'll point that out in the next slide. This is just the tangential acceleration. So when you put a torque on something like that baseball bat's going to accelerate in the direction of that torque. Now, the further out you are from the axis of rotation, the more acceleration you're going to have. So AT, the tangential acceleration, is dv dt, which is r times d omega dt, which is r times alpha. Okay. Notice, you can get, if you know omega, you can get the speed by multiplying by r. It'll tell you how fast it's going at different points on the object. If you want to know the acceleration at a point on the object, you take the angular acceleration and you multiply by r. Because remember, omega and alpha are the same for all the points that are rotating, because it's a rigid body. It's a rigid body. Okay, so over here, you see, you always have a inward acceleration because the body's got to maintain integrity. So you don't want it to break up into a bunch of little bits. So it has to have a centripetal force to keep all those molecules in place. So I put a little video in the preview PowerPoints where this guy spins a CD at a super high omega, and the CD just disintegrates. Well, that means he went so fast that there wasn't no longer enough force to provide the centripetal acceleration to hold the CD together. But when he put the torque on the disc to make it go faster and faster and faster, that was the acceleration tangential to the circle that in the lab. Tangential acceleration. You can ignore the centripetal acceleration. Nothing's going to disintegrate in our lab. We're not spinning things that fast. All right. Now, if you go back over here, you can see the force for the tau net, it's r times 4 sine theta. Well, the force can produce some really crazy acceleration. So if you have a constant force, then you can just go to these equations. Recognize these equations? This is for constant force. Well, what if you have constant torque? Well, then you're going to have linear angular frequency. Your theta is going to increase as a square function of time, and then the alpha will be a constant acceleration. So these are all of our kinematics equations applied to constant torque. So when you have a constant torque, they follow the same equations, but only for the angles instead of V, X, okay, A. Now we've got theta, omega, and alpha. All right? And you can go from one to the other, depending on how far away you are from the axis of rotation, by multiplying by r. R times theta is S, okay? R times omega is V, and R times alpha is A, the acceleration. Okay, and that's it. That is the background on the experiment we're doing. So this is just to alert me that I'm done talking about the background. So we're going to stop there and start another one and show you the experimental setup and what you're going to be doing in the lab. So peace be with you, and we'll see you very shortly. Bye.